Good evening. In this lecture, we're going to talk about multipole expansion. Recall that we previously discussed multipole expansion at length, but we're going to revisit this because now we have developed newer methods to solve the Laplace equation and in general find out phi. Especially we developed this new method of separation of variables, and in general, by setting del square phi is equal to 0, the general solution that we found in spherical polar coordinates was something like phi of r theta is equal to sigma L is equal to 0 to infinity AL r to the power L plus BL by r to the power L plus 1 times PL of cosine theta. For problems with azimuthal symmetry. If you don't have azimuthal symmetry, then you add an extra term e to the power im phi here, and the product becomes the spherical harmonics ylm theta phi. All right. So in general, we can define spherical harmonics. We did this in previous lecture. So in general, if you have phi dependence, azimuthal dependence, instead of Legendre polynomials, then you would have ylm theta phi, which would be some constant L minus m factorial by L plus m factorial PL m of cosine theta e to the power im phi. So if you have phi of r theta phi, then you would have in general L is equal to 0 to infinity and m is equal to minus L to plus L, then this entire r term comes here, right? So you have AL RL plus BL by RL plus 1, and then this term. And then this term is for theta and phi. ylm theta phi is the solution for both theta and phi in general. But in the last few lectures, we were specifically looking at situations where there was azimuthal symmetry. And now we are going to apply this to the problem of multipole expansion. So to do that, first we will go back to how we define the potential of any arbitrary charge distribution. So if I have some arbitrary charge distribution, then I can divide this into tiny parts, right? I can divide this into tiny parts, and I can start from the origin. Start in this cell, and go around counting each cell, right? And I'm interested in finding out, let's say, the potential at some point here. Then we connect that from the origin. We call this R, and we call this R prime. So we are integrating over R prime, right? And the angle between R prime and R is what we call as theta. And this distance would be R minus R prime. So the potential here, we have seen previously that in general the potential phi, the scalar function phi, would be equal to volume integral over r prime, because we are going around each of these cells, and that variable is r prime. So when we change r prime, what we're saying is that the arbitrary charge distribution that we have divided that into tiny cells, and we are looking at potential of each cell. So each cell would have a total charge of the charge density times the volume, and the distance between this and the point P would be r minus r prime. So you would have r minus r prime. So this was our, in general, the definition of the potential. And previously when we studied multipole expansion, what we did was we considered this term in the denominator. We considered only 1 over r minus r prime, and then we did a Taylor series expansion. And that's how we got our different terms for monopole, dipole, and quadrupole, so on and so forth. We're going to do a similar thing here, but we're going to do that using the spherical polar coordinate solutions. So to do that, we are going to consider this function 1 over r minus r prime. So let me rewrite this function. I'm interested in looking at this function 1 over r minus r prime, which is what we Taylor expanded. We performed a Taylor series expansion for studying multipole moments, and now we are just trying to look at it a little different way. So if I look at a potential that looks like this, right? This satisfies clearly the boundary condition that phi of r goes to 0 as r goes to infinity. And so we can think of this as some unit charge, right? So traditionally we have some here a term kq if you have a charge q. So if we have just term, so let me rewrite that. So in general, so the general expression for phi of r is, it would be kq by r minus r prime, right? R prime is the location of the charge q, right? So if you have a charge, let's say, that is located here, q, right? And let's call this r prime, right? And let's say we're interested in some point P here. And so from the origin to P is R. And so from Q to here is R minus R prime. So the potential from this charge at P would be KQ by R minus R prime. But we are interested in expanding a function that is 1 over R minus R prime, right? So we're going to look at a charge that is 1 over K. So when you do KQ gives you 1. So just imagine that you have some charge like this, 1 over K, right? Or in some system of units, you can also set K is equal to 1. And then at the end we can multiply with K again whenever we finish the derivation. So if we set K is equal to 1, you can think about this as potential from a unit charge. Right. So now let's say there is this unit charge that is here at r prime, and you have r, then the potential at point P, is given by this. And if we call this angle as theta, right, then I can in general write in spherical polar coordinates phi of r theta in spherical polar coordinates as sigma L is equal to 0 to infinity AL r to the power L plus BL by r to the power L plus 1 times PL of cosine theta. Here we are not writing the phi term in this expression because we are supposing that this unit charge, whatever that is, we are supposing that it is located along the z-axis. So we are aligning our z-axis. We are aligning our z-axis with the charge here. So we are aligning our z-axis with the charge. So that's why, because our charge is along the z-axis, that's why there is no phi term. So that's why we are writing phi of r theta in general as sigma L is equal to 0 to infinity AL r to the power L plus BL by r to the power L plus 1 PL of cosine theta. Once again, to take a step back, what we are trying to do here is perform a multipole expansion. We have already done this before by applying Taylor series on this one. However, here we now want to use the general result, the general solution that we got in spherical polar coordinates, that is this, to see how we can do Taylor expansion and use the separation of variables. So then now if this is the general solution, then theta would be the angle between r and r prime. So if we look at a boundary condition would be phi of r, theta is equal to 0. So this boundary condition would mean all the points along z-axis, right? If I set theta is equal to 0, then I'm basically talking about all the points along this axis, right? So for all the points along this axis, it becomes a one-dimensional problem, because if I redraw it, we have the z-axis, and I have some charge q, some unit charge, let's say q is equal to 1 at a distance r prime. And if I'm interested only in potential along z-axis, it's a simple one-dimensional problem, right? So depending upon where my point is, if my point is anywhere along the z-axis, so I can write that as r. So if I'm interested in a point P here, then again, this is simply just r minus r prime. This is not r vector minus r prime. Here we have r vector minus r prime. That means this r has r, theta, phi, 3 components, right? Here what we are saying is we are specifically considering the points for theta is equal to 0, because we want to use that as a boundary condition for the multipole expansion. And when we say theta is equal to 0, then we are considering all the points along z-axis. So for all the points along z-axis, both the vector pointing to the point of interest P and our charge, both are along z-axis. So this is not a vector. This is just the component along z minus the other one. So both P and the Q, both the charge and the point of interest, both are along the same axis. So this is not a vector. So that's what you should take a note. So then in this case, then this would just simply be 1 over r minus r prime. Once again, these are scalars, no vector here, because we are along the same axis. So then I could write this then as 1 over, I could pull out r as a common factor, and I have 1 minus r prime by r. And if r prime by r is very small, if r prime by r is small, then we know that from Taylor expansion, if you have something like 1 over 1 minus epsilon, for small epsilon, for small values of epsilon, you can write this as 1 plus epsilon squared plus epsilon cubed, so on and so forth. So here we have 1 minus r prime over r. So our epsilon is r prime over r. So I can write this as 1 over r times 1 plus r prime by r plus r prime by r whole square plus r prime by r whole cube, so on and so forth. Again, note that these are scalars. These are just the components, because now we are considering only those points along theta is equal to 0. That means only those points that are along the z-axis. So then this is our boundary condition, right? So in general, what we are trying to do is we have some system and we have some charge q, which we are saying is a unit charge that is at a distance r prime. In general, if we want to look at any theta, right, then that would be equal to sigma L is equal to 0 to infinity AL RL plus BL by RL plus 1 times PL cosine theta. And we said that there is no phi dependence because Q is on z-axis, or we are setting m is equal to 0. So the z dependence, if there was phi dependence, we would have a factor that would look like e to the power im phi. And if our charge is along the z-axis, if we pick wherever the charge is, if we pick that as the z-axis, then we can set m is equal to 0, or this term wouldn't appear, right? So you have only dependence on r and theta. So the charge is along the z-axis, but the point of interest, that is the point where we want to find out potential, could be anywhere, right? For example, if this is P, right, this could be anywhere in three-dimensional space, right? So this is the general solution for any point in three-dimensional space, denoted by r theta, right? And there is no phi dependence, so it's independent of phi. Then the boundary condition we came up with was phi at r and theta is equal to 0. That is, if you look at just the points along this line, along z-axis. And that boundary condition we saw came out to be 1 over r minus r prime. These are not vectors, these are scalars, because when we are considering theta is equal to 0, this is the theta, the angle between r prime and r. So when they coincide, when everything is along z-axis, then there is no, these are just the components that you're subtracting. And we saw that we can do this as 1 over r times 1 over 1 minus r prime over r. And then we Taylor expanded this to get 1 over r times 1 plus r prime by r plus r prime by r whole square, r prime by r whole cube, so on and so forth. So this is our boundary condition. So then we can go ahead and look at our general solution and apply our boundary conditions. So one boundary condition is definitely that as r goes to infinity, we need phi to go to 0. So because of that, we'll have to set this term to 0, because otherwise if we have al r to the power l, we would diverge, right? And similarly, then we have phi of r theta by applying the first boundary condition would be sigma l is equal to 0 to infinity bl by rl plus 1 pl of cosine theta. So then if we look at this boundary condition where we want phi of r theta is equal to 0, then that means I would have to write L is equal to 0 to infinity BL by RL plus 1 PL of cosine 0, because we're setting theta is equal to 0 for this boundary condition. So then that is just PL of 1. So because cosine 0 is equal to 1. So we can find out what this PL of 1 is from the generating function. So PL of x in general is 1 over 2 to the power L, L prime, d by dx to the power L, x squared minus 1 to the power L, right? So if I have PL of 1, that would be 2 to the power L, L prime, right, d by dx to the power L of 1 square minus 1 to the power 0, right? And there is this dx, d by dx, right? This is also 1, so there is no change. So irrespective of which function you pick, which L you pick, PL of 1 is always equal to 1. So PL of 1 is equal to 1 for all L. That is the property of Legendre polynomials. So this term is just really 1. So we have this then. So then I can write phi of r theta is equal to 0 by applying the boundary condition to our generalized potential. I get L is equal to 0 to infinity BL by RL plus 1. But the boundary condition that I derived from here is this, that is the phi at r and theta is equal to 0. So we can plug that in. So this should be equal to 1 over r times 1 plus r prime by r plus r prime by r whole square plus r prime by r whole cube, so on and so forth. So here, from this, I can take out 1 over r and write this as sigma L is equal to 0 to infinity BL by r to the power L, and here I would have 1 over r plus r prime by r plus r prime by r whole square plus r prime by r whole cube. So here I would like to take a minute and point out what we are doing here, because it's too mathematically rigorous. I don't want you to lose the way. So we started with the general solution in spherical polar coordinates, and we applied boundary conditions, that is, that the potential should not diverge as you go to infinity. And from that boundary condition, we saw that only B part from this term here, only this sustains. And then we saw that when we set theta is equal to 0, because we derived a specific boundary condition for phi is equal to r theta is equal to 0, that is the second boundary condition. So when you apply that, all the Legendre polynomials become 1, because that's a property of Legendre polynomials. PL of 1 is defined to be 1 for all L. So essentially we end up getting as this. So when we apply the boundary condition on the general solution, we get that this term should be equal to the potential at theta is equal to 0. Right? And we derived this from just physical considerations by looking at the z-axis and doing a Taylor expansion. So then by comparing each term here, then you can see that each term for L is equal to 0, you would have B0 by r to the power 0, or you would just have B0. So that should be equal to 1. For L is equal to 1, you would have B1 by r, and here you have r prime by r, or that implies B1 is equal to r prime. For L is equal to 2, this is a series of terms. For L is equal to 2, you would have B2 by r square is equal to r prime square by r square. So that means it implies B2 is equal to r prime square. So you can see B0 is equal to r prime to the power 0, B1 is r prime to the power 1, B2 is r prime to the power square, or in general BL is r prime to the power L. So by applying the boundary condition phi at r and theta is equal to 0, we figured out what the coefficient should be. So then we can go back. Our original potential in general, phi of r theta, we wrote as 1 over r minus r prime. Here, notice that these are the vector signs, because now this theta is equal to 0 is a special case when both the point of interest and the charge are along z-axis. So these r's are just the scalars. But in general, if you don't have theta is equal to 0, if you cover all the thetas, then these would be vectors, right? And we were able to express this as L is equal to 0 to infinity BL of by r to the power L plus 1 PL cosine theta. In the boundary conditions, these PLs went away because we set theta is equal to 0. So they went away only for theta is equal to 0. For other thetas, so the boundary condition is one specific location, so we're picking out one specific line. So that's why don't get confused between the expressions that we write in general for r and theta versus the expressions we would write for r and specific values of theta. So when we wrote for theta is equal to 0, there is no Legendre polynomials here because we are setting cosine 0 to 1. But in general, that term would be there. But we figured out from the boundary condition, we figured out that BL is simply r prime to the power L. So then I can write this as sigma L is equal to 0, right? 1 over r, r prime over r let me rewrite that. Let me rewrite that in a different way. So what we are going to do is, so underneath BL we have r to the power L plus 1. So I'm just going to pull one r out. So I would have L is equal to 0 to infinity, right? BL by RL, PL of cosine theta. And BL is r prime to the power L. This we got from the boundary condition. And the boundary condition is phi at r is equal to theta is equal to 0 was 1 over r. This is scalar again, plus 1 plus r prime by r plus r prime by r whole square, so on and so forth. This was the boundary condition that we applied to get BLs. So then I can write this as 1 over r sigma L is equal to 0 to infinity. BL is simply r prime to the power L, so I would have r prime by r whole to the power L PL of cosine theta. Right? So now we got this relationship that 1 over r minus r prime is equal to 1 over r sigma L is equal to 0 to infinity r prime by r PL of cosine theta. So we got this relationship. So what we are trying to do again in the big picture is we're trying to do multipole expansion using spherical polar coordinates. So we started with the general solution, we applied the boundary condition, and we figured out that 1 over r minus r prime is this. Previously, to figure out an expansion for 1 over r minus r prime, we simply did the Taylor expansion. That Taylor expansion is not the same as this Taylor expansion here, because once again, I have noted this several times, and I'd like to note this again. Here also we did a Taylor expansion, but notice that this Taylor expansion we did only for the boundary condition where we set theta is equal to 0. So this r and r prime are not vectors. In the previous lecture, when we first studied multipole expansion, we did a Taylor expansion of the vectors. So that's the difference between the Taylor expansion we just used and that we previously had done. So instead of the Taylor expansion, in this case, today in this lecture, using spherical polar coordinates, we figured out that this function 1 over r minus r prime vector can be expanded in terms of its components like this. So here you have vectors. These are r component, this is theta component. Right? So those are the components. So that's a distinction that you have to make. So now we have gotten this important equation. So we can go back to the potential of an arbitrary body, right? So like I explained in the beginning of this lecture, if I have some point P here, this is r, and if I go around with r prime, then I can write phi of r as k times d cube r prime rho of r prime by r minus r prime. Right? That's in general the potential. But now we figured out that 1 over r minus r prime could just be expanded as 1 over r sigma L is equal to 0 to infinity r prime by r to the power L PL of cosine theta. So instead of this 1 over r minus r prime, I could plug this in. So then my phi of r would be k times d cube r prime rho of r prime times 1 over r, right, sigma L is equal to 0 to infinity r prime by r whole to the power L PL of cosine theta. And we got this expression by doing the boundary conditions. Now this integral is over r prime, correct? So or this r and this r prime are different. So I could then see that this r and this r could be pulled out because they don't depend upon the integral, right? So then I can write this as k. So I'm going to pull the summation first. So the summation is going to be L is equal to 0 to infinity. So this is just a series of terms. So we're just multiplying this with each term in this series and integrating. So then I can write it as, so if I have integration of rho of r prime d cube r prime with a series of terms that look like some 1 plus 2 plus 3, these terms. So instead of writing this sum later and the integral first, I could take this and multiply each term and write it as a sum of products. So that's what I'm doing. I'm writing it as a sum of products. So the sum is going from L is equal to 0 to infinity, and inside I have 1 over r and r to the power L plus 1. This doesn't depend upon the integral r prime, so it's outside. And then I have integral d cube r prime rho of r prime. So we just basically put in all the terms that have r prime dependence, r prime to the power L PL of cosine theta. Now you may be wondering why PL of cosine theta is in there if the integral is over r prime. So this is a volume element. That means we are going over this theta. We're changing this theta as we are going from one point in the body to another point. We're changing that, and because the angle with respect to point P, the angle between this vector and this vector is going to change. So that's why this is still inside the integral. So I'm going to rewrite this expression hash on the next slide again. So then I have phi of r is equal to essentially what we got is sigma L is equal to 0 to infinity. R doesn't depend upon the integral because we're going around. This r prime is within the body, so we are integrating from one part of the body to another part of the body. All that we did was just substituted an expansion for the term 1 over r minus r prime to get this. So r prime to the power L PL of cosine theta. This is what we got. This is what I wrote as the pound key, right? So then now I can just write this as a sum. So if I look at for L is equal to 0, this is just a series of terms that are added one after another. So if I look at L is equal to 0, then I can write that as phi L is equal to 0 of r would be 1 over L is equal to 0 would give me 1 over r d cube r prime rho of r prime. L is equal to 0 means this term is just simply 1, and if L is equal to 0, P0 of cosine theta is simply 1, right? So then I have just this, because this is 1 and this is 1 for L is equal to 0. And this is what, if you remember, we called as the monopole term. Right? So now we can also look at for L is equal to 1. For L is equal to 1, phi L is equal to 1r would be 1 over r squared, because L is equal to 1, times, so I'm plugging in L is equal to 1 in this expression. We're singling out each term because we want to look at each multipole term. So this is a sum of multiple terms, and each term is a part of that multipole expansion. So when we set L is equal to 0, we get the first pole of the multipole, that's the monopole. And when we set L is equal to 1, we get the second term, which is the dipole term, right? So that would be d cube r prime rho of r prime P1 of cosine theta. So P1 of cosine theta is P1 of x is simply equal to x. So this is equal to simply cosine theta. So instead of that, we can write 1 over r squared d cube r prime rho of r prime cosine theta. Right? So now if you go back and look at what is r prime cosine theta, we have the arbitrary charge distribution here. R prime is the location to one particular part of the charged body, and R is the location to point P. and the angle theta is this. So if I look at r unit vector r dot r prime, then that would be simply r prime cosine theta, right? Because r is a unit vector, it won't feature here, it's just one, and r prime is the magnitude is r prime, right? The magnitude r prime times cosine theta, which is what we have here, right? So then I can rewrite this as 1 over r squared r dot d cube r prime rho of r prime r prime. So I change this to a vector because r dot, I'm dotting it with r dot r prime, would give me r prime cosine theta. So now what we're going to do is we're going to define this integral as the dipole term. And we call that as dipole moment P. So then this can be written as 1 over r squared r dot P. Right. So we're simply expanding each term in this series, and we figured out the monopole term. We got the dipole term. So similarly, now you can do for L is equal to 2 as well. So L is equal to 2 is would give us, so in general we have the sum phi of r is equal to, we found that it is L is equal to 0 to infinity 1 by r to the power L plus 1 integral d cube r prime rho of r prime to the power L PL of cosine theta. So if I put L is equal to 2, then phi L is equal to 2 of r would be just, I'm going to take the L is equal to 2 term only. So I have 1 over r cube because L is equal to 2, and then d cube r prime rho of r prime cube, r prime square because L is equal to 2, and P2 of cosine theta, right? And P2 of cosine theta is equal to 1 over 2 3 cosine square theta minus 1. That's the value. We remember that we had a generating function for the Legendre polynomials. We actually calculated what Legendre polynomial should be, P0 of x, P1 of x, and P2 of x in the previous lecture. So if you have forgotten, go and revise that to see how P2 of cosine theta is this. So if I plug this in here, then that would be equal to 1 over r cube d cube r prime rho of r prime square half times 3 cosine square theta minus 1. And now I can rewrite this by taking r prime square inside. So I would have 1 over r cube d cube r prime rho of r prime half of 3 times r prime square cosine square theta minus r prime square. Now recall that our charged body is here, so a point is r prime here, and this is r, and the angle between them is theta. So we saw that r unit vector dot r prime is r prime cosine theta, and here I have r prime cosine theta square. So I could instead write this as rho of r prime half 3 times r dot r prime whole square minus r prime square, right? So then I can manipulate this further. I have 1 over r cube. Now if I were to pull out an r as a common factor, so in the previous example we had r prime cosine theta, but we had only one term, so we could pull r dot outside the integral. Recall that this integral is over the charged body, So it includes only r prime. It doesn't include r. That's why we were able to pull this r out. But here we had only one term, so it was easy to pull the dot product out. But here, if I want to do a similar thing here, then that's going to be difficult. We saw that this is equal to 1 over r cube integral dou cube r prime rho of r prime half 3 times r dot r prime square minus r prime square. So it's going to be hard to pull out just r dot. So what we have to do is, this is actually a tensor integral, not a vector integral. So we write it as 1 over r cube. I pull out an r dot on this side, and then write this as d cube r prime rho of r prime. So because I pulled this out, I would have half times 3 r prime, right? Because I have r prime square, and minus I have r prime square, but I have pulled out an r dot, so I have to somehow make up for it. So I just multiply with an identity matrix, and then we multiply with r dot, the r unit vector here again. So that's how we will be able to pull out the r dot as a common factor. So if you want to pull r as this r, the dot product with r, if I want to pull this out as a common factor, I need to do it from both sides, because the second term r prime square doesn't have any dot product in it. So that's why I'm dotting it on this side, so that I can get back to this expression. So this is how I can write it. Or in other words, then I can write this integral as a quadrupole integral. This is a tensor, because you would have 9 components. You have 3 components for each vector, and then you have a product of one vector with another. So you are essentially doing 3 times 3. So you have 9 components, or you have a 3 by 3 matrix in this, because you have to go over each component. These are vectors, so you have to go over each component of those vectors. So you actually have 9 components, right? If I were to rewrite this for phi L is equal to 2, it would look like 1 over r cube r dot integral d cube r prime rho of r prime half 3 r prime, these are vectors, minus r prime squared, this is not a vector, times an identity matrix, and here dot r again. And so this is what we are calling as the quadrupole moment. So in general, then, we can write phi of r as the monopole term, which is just q by r, and the dipole term, which is p dot r by r squared, and the quadrupole term, this is the quadrupole term, and that would be 1 over r cube, r dot on one side, r dot on another side, and in between we have the vector q. So this would be how multipole expansion looks like when we do it in the spherical polar coordinates, right? So now we can quickly also look at another thing, right? So to do that, we have to go back to this expression, which we derived from the boundary condition. I know that this is a lot of math that is going on. I'll try to upload typed notes so you can follow this through. And so if we go back to this equation here, we can rewrite that here. We had phi of r is equal to L is equal to 0 to infinity 1 over r to the power L plus 1 integral d cube r prime rho of r prime to the power L PL of cosine theta. This is what we had. We got this r prime L from BL, right? So if you look at this PL of cosine theta, right? PL of cosine theta, we can in general write this in terms of spherical harmonics. So what we're going to do is spherical harmonics, recall that spherical harmonics have two parts, theta and phi, the coordinate phi, and the theta part is the Legendre polynomial, and the phi part is something like e to the power im phi. Right. So if you take the complex conjugate of a Legendre polynomial, you would get, this would remain still, this is real, PL of cosine theta is real, right? And this is imaginary, so you would get e to the power minus im phi. So if you multiply a spherical harmonic with its own complex conjugate, then you can see that these terms would cancel out, and you can get just the PL of cosine thetas. So if I, in general, have, let's say, a charged body, and if I have, let's say this is my r prime, and let's say this is my r prime is within the body again. So I'm going to call the angle of z-axis to r prime as theta prime, and similarly phi prime for r prime, that is within the body, and for the point of interest it would be theta and phi. So then I can write this PL of cosine theta as 4 pi by 2l plus 1. This is just a linear combination of m is equal to minus l to plus l. So we are adding over m, so these em phi terms are getting cancelled out. So we are left with only the Legendre polynomial. So we can write that as y lm star theta prime phi prime times y lm theta phi. So I can then plug this into the expression for phi, and then what I would have is phi of r would be sigma L is equal to 0 to infinity, and now I have another sigma that goes from m is equal to minus L to plus L, and I would have 1 over RL plus 1, and then I have this factor 4 pi by 2l plus 1, which comes from the linear combination term. That's just there to make sure that the orthogonality relationship is normalized. That is, when you do the integral, you get 1. So then I have here an integral that goes from d cube r prime rho of r prime to the power l, and then I have these ylm star theta prime phi prime and ylm theta phi. So the integration is only on the primed coordinates, that is, it is over the body. So you can take this term and call this term as qlm. Then we can rewrite this as L is equal to 0 to infinity, m is equal to minus L to L, 4 pi by 2l plus 1 times r to the power l plus 1 qlm, and here we have just ylm theta of phi. So in general, for any arbitrary charged body, so if I have just some charged body here, right, then I can write the potential due to the charged body in spherical polar coordinates as 4 pi sigma L is equal to 0 to infinity, m is equal to minus L to L. So this is like having a nested loop. So if you have for L is equal to 0 to infinity, for each L you have a sub loop where you're going from minus L to plus L, right? And then you have QLM times YLM theta phi by 2L plus 1 r to the power L plus 1. So this is in general the expression for potential at some r from any arbitrary body, and this QLM is what has the information about how charge is distributed over the body. We define this QLM as the integral dou cube r prime, rho of r prime to the power L, YLM theta prime phi prime, right? So this has all the prime coordinates, and it has all the information about the shape and the distribution of charges. And so in general, we can write for any potential, we can write this as a series of terms. And when we look at the series of terms, we have L going from 0 to infinity. So for when L is equal to 0, we get the monopole term. For L is equal to 1, we get the dipole term. For L is equal to 2, we get the quadrupole term. And one thing that you may have seen here is that the monopole term goes as R, the dipole term goes as R squared, and this goes as R cubed. And so really, if you look at higher order terms, they would be going as R to the power 4, R to the power 5, so on and so forth. So as you go even little farther from the charged body, these terms really become very, very negligible, right? And because they become very, very negligible, they go away, and you can approximate the total potential just using the first three terms. And when you do the gradient, right, this is just the potential. So to get the electric field, you have to do another gradient. So you know, these powers would even be smaller when you do the gradient, right? And then so you can ignore these higher order terms in general, and you can just compute this. So in general, from the multipole expansion like this, we can in general calculate any potential for any charge distribution and obtain the electric field by